Hello, my name is Theo Lack, and in this video, I'm going to be talking about the rocket that was launched, you can see on the right here, during the summer of 2025. This is a liquid oxygen powered hybrid rocket launched by Columbia Rocketry, and this year was our first club experience with liquid oxygen, with cryogenics, and with regulated pressure, and we successfully designed, built, and launched this rocket in 1 year. This is a view of the fluid system when the airframe is removed. This is about here on the rocket. The goal of this video is to explain this entire diagram. The goal is by the end of this video, you will understand generally what every component does and why it's necessary in order for the rocket to function safely. This is the piping and instrumentation diagram, also called the PNID. First, I'm going to give some basic background about pressure and flow. Let's say you have a collection of particles that have a random velocity in this box. We would say that this volume has higher pressure and this one on the right has lower or no pressure. If you removed this panel in the middle and then came back at a later date, you would expect particles to evenly distribute and also flow from the left side to the right side. In other words, the net flow was from higher pressure to lower pressure. If instead you consider a pipe of, let's say, water, if you have a net flow of water from the left to the right, in general, that means you have a pressure gradient from the right to the left in the opposite direction. So in other words, you have higher pressure upstream where the fluid is coming from and lower pressure downstream where the fluid is going. And you need this difference in pressure in order to drive the flow. If you replace this pipe with instead a model of a rocket, this is a model of a hybrid rocket. And this is the back. So this is where the exhaust comes out of. You need very high velocity exhaust in order to generate thrust because of conservation of momentum. To get the highest velocity exhaust, you need very high pressures in the combustion chamber. And this is in order to accelerate the gas to a very high pressure through the nozzle. But as we discovered before, in order to deliver the liquid oxygen, which is the oxidizer, into the combustion chamber, you need an even higher pressure upstream. So that's where the higher pressure liquid oxygen tank comes in. And the entire role of the fluids team is everything upstream of the injector. So it is our role, it is our job to deliver the very high pressure liquid oxygen into the combustion chamber. The pressures that we're working with are about 50 times atmospheric pressure. If we flip this rocket vertically, we see that this is our basic diagram, and this is correspondingly what it looks like in reality. At the bottom, we have the combustion chamber and nozzle. This is where the flamey end, where all the gas comes out of, and this is the corresponding combustion chamber on the rocket. This shrouded portion is the run valve, and this white tank is the liquid oxygen tank. Inside the airframe up here, we have the COPV and the other fluid system. In our rocket, we have a combustion chamber pressure of about 500 psi at launch. In order to deliver this 500 psi, again, we need a higher pressure upstream. So our liquid oxygen tank is about 700 psi. And in order to push all of that liquid oxygen down, we have an even higher pressure in the COPV, which is 4,000 psi. COPV stands for composite overwrapped pressure vessel, basically just a very high pressure tank that holds pressurized gas, in our case, nitrogen. The first component on the diagram is the run valve. This is one of 3 custom cryogenic valves that we designed and machined this year. This valve is normally closed. That means that there's a spring inside the valve which is holding it closed and sealing. This is very important because we want to make sure absolutely no liquid oxygen comes down into the chamber before we launch. And once we launch, we can pneumatically actuate it to open and deliver the liquid oxygen. Pneumatically actuating just means that we inject pressurized gas into the side of the valve, and that pushes up the piston and opens the valve. Obviously, the rocket can't function on its own like this. We need some connections to the ground to fill it with propellant. In our case, our propellant is liquid oxygen, and the pressurant gas is nitrogen, gaseous nitrogen. To do that, we have 2 umbilical connections. The first is a connection to the liquid oxygen tank to fill liquid oxygen, and the second is a connection to the COPV to fill nitrogen. And we also have a vent that vents the liquid oxygen. Both of these valves are the second and third valves that we designed and machined, and they are both normally open. which is different than the run valve, which was normally closed. Normally open just means that under regular conditions, the spring is pushing it open. Liquid oxygen, we fill from what's called a dewar. This is a liquid nitrogen dewar, but this is used for testing. But for launch and static fires, we need to use liquid oxygen. This is a very well insulated cylinder that has liquid oxygen in it. And we connect it to the rocket through a fitting on the dewar, and we connect it manually and disconnect it manually to our fill valve. As you may know, liquid oxygen and liquid nitrogen are cryogenic fluids, which means they're incredibly cold. They are about negative 200 degrees Celsius. What this means is that they cannot survive at ambient temperatures. And in fact, as we fill the tank through our normally open fill valve, we fill the tank, but since the environment is so hot compared to the liquid oxygen, a little bit is always boiling off. And without a vent, this liquid oxygen that keeps boiling would keep pressurizing the tank, and eventually it would explode or otherwise fail, and the liquid oxygen would escape. So this is simply because liquid oxygen cannot survive at ambient temperatures. It needs to be cold. This is why it's important to have a vent. And in our case, we have a continuously open vent. So this is essentially a hole at the top of our tank for now, that as we fill the tank slowly, a little bit of the liquid oxygen will be constantly venting from the vent valve. On the other hand, our gaseous nitrogen is not cryogenic. It is simply comes as pressurized gas in a cylinder like this, and that is connected to our ground station, which I'll talk about later. And when we want to fill, we fill it through this line and into the COPV. Now, as drawn, this system would not function. We cannot simply connect our COPV to our tank. Since our COPV, if you remember, is all the way to 4,000 psi, while our tank is only designed to be 700 psi. So we need a component to regulate that pressure from 4,000 to 700. And to do that, we have a dome-loaded regulator. We also have a pilot regulator, which is a spring-loaded regulator, which regulates the pressure down from 4,000 all the way to 700 psi. This is to actuate our pneumatic valves, as well as to be connected to the dome-loaded regulator to allow flow to go into the tank. This is a simplified diagram of how a regulator works, in this case a spring-loaded regulator. If you start pressurizing the inlet, the pressure is free to flow through this opening and down to the lower pressure. But once the outlet reaches a certain pressure, it will push up on this diaphragm enough where this poppet will move up and it will seal, basically stopping any more pressure from going in. In practice, this means that ideally you have a set regulated pressure, and that if your inlet pressure is any higher, it doesn't increase the outlet pressure. So this is how our spring-loaded regulator works. Our dome-loaded regulator is a similar concept, but instead of having a spring, you have an open cavity which is pressurized with gas. The first connection we need for a pilot regulator is to close our fill valve. So once we're done filling liquid oxygen, we can't just disconnect the line, because then liquid oxygen would pour out of this valve. So we need to close this valve in order to disconnect it and move the dewar away. To close it, we connect it to the outlet of the pilot regulator, so that when we pressurize the COPV, at first we only pressure it to about 700 psi, and that is regulated through this regulator, and that closes our fill valve and allows us to disconnect the dewar and move it away. But there is one issue with this system. In the case that something goes wrong and we need to abort, we need the capability to be able to dump all of the propellant from the vehicle. And we have an ability to do that from the panel. So we can electronically dump all of the pressure from the COPV, but this regulator does not backflow. What that means is that even if the upstream, even if the inlet is depressurized, the outlet will remain pressurized, and this fill valve will remain closed. So what we need is a way for the pressure to leak from the outlet back to the inlet, so that when we abort, the fill valve will open and the liquid oxygen will drain out of the tank. This isn't a safety issue because our vent valve is normally open, so this will still be venting liquid oxygen continuously, but we would have to wait until all the liquid oxygen has boiled off from the tank, which could take a significant amount of time. In order to rectify this, we attach what's called a check valve between these two lines. A check valve is a straightforward valve that this version involves a ball and a spring, and it essentially acts as a one-way valve. So you can imagine if pressure comes in from the left on the top here, it will push the ball open and it will flow through. But if it comes in from the right, it will simply push the ball even further closed and it won't be allowed in. So this check valve is arranged such that flow can go upwards but not downwards. So this ensures that when we depressurize the COPV, the fill valve opens and the entire system is drained of propellant. The next connection we're going to look at is the run valve. So after the pilot regulator, we have what we call the run pilot solenoid. And this is a solenoid valve. And you can see from this diagram here that it's an electronic valve. When you connect this circuit here to this essentially copper coil, it forms an electromagnet. And it raises a poppet up, which allows fluid to flow. And it's pushed down by a spring, so this is normally closed. So with no connection applied, this is closed. And this is what we want in this case, because when there's pressure that's going through this line, this will open our run valve and it will allow flow into the combustion chamber. And we only want this to happen during launch and definitely not earlier. Our second solenoid on the vehicle relates to pressurizing the tank, and we call it dome pilot. So it has two connections. The first connection is to the dome-loaded regulator, and that's where it gets the name dome pilot. So when the dome pilot, when the pressure flows through this line and goes into the dome-loaded regulator, it pressurizes that cavity above the diaphragm, and it essentially primes this dome-loaded regulator, and it allows gas to flow from the COPV into the tank. This will pressurize the tank, and it will be ready for launch. But this vent valve, unless we close this vent valve first, all that pressure will simply leave through the vent, and we won't get anywhere. So that's why we also need it to connect to the vent valve and close it. Now, when we first implemented this, we just had these two connections, and we didn't have this device here. These two lines here represent an orifice, or basically a very small hole that separates these two sections of pipe. And what this does in practice is that the section of tube upstream of the orifice will pressurize much faster since it has no obstruction. So this means our vent valve will close very quickly after opening the dome pilot solenoid. And then after about 2 seconds, the line after this orifice will pressurize fully, and that will allow flow to go through the dome-loaded regulator and allow us to pressurize our tank. In case another safety mechanism we have is that if anything goes wrong with the dome-loaded regulator or it fails somehow, we have a burst disc attached to the tank. And what a burst disc is, it is a very finely manufactured product that is designed to break and allow flow through at a very specific pressure. In this case, just over 1,000 psi, which is higher than our expected tank pressure of 700 psi. So this ensures that even if something unexpected happens or something goes wrong, that our tank can't burst, because this will break before the tank does. Now, in order for the rocket to launch, this is technically all we need for it to be functional. But in practice, especially during testing, we want a bit more flexibility and control over the system. So we have an ability to vent both of these piloted lines, the run pilot and the dome pilot. And that looks like this. So you can see that the run pilot is connected through this check valve and the dome pilot is connected directly. And this is another solenoid that we can command electronically to open. And this is important because if you imagine either of these two solenoids here, the run pilot or the dome pilot, if either of them are leaking just a little bit over the 20 or 30 minutes that they need to seal, for example, if the run pilot leaks a bit, then the run valve might eventually open, which could be very bad because that might prematurely launch the rocket. Or if the dome pilot is leaking a bit, that could prematurely pressurize the tank, which is also something we don't want. So we want to be able to vent these lines. This check valve here is a way of connecting both lines to the vent without connecting the lines themselves. So because during our launch operations, we pressurize the tank before we launch, because we want our tank to be fully ready to go by the time we launch. The dome pilot opens before run pilot in our sequence. And this check valve ensures that even if the dome pilot line is pressurized, it won't go towards the run pilot, while still allowing flow to go up through the check valve and vent off. Finally, in order for successful testing and making sure everything is working properly, we need to have sensors. So in our case, we have 4 sensors. We have 3 pressure sensors and a temperature sensor, and these are electronic components that we can read remotely. So we have a pressure sensor on the COPV, we have one on the tank, and one on the combustion chamber. We also have a temperature sensor for the COPV. And this is important because when you fill the COPV, you're putting extreme amounts of energy in there because you're compressing so much gas in order to put in there. And that energy or enthalpy that you add will increase the temperature. And we need to make sure we don't go above the rated temperature of the COPV, which is about 60 degrees Celsius. So this thermocouple, which is embedded in the line, is to make sure that doesn't happen. Now that we have all the components on the rocket, we have a couple more safety-related components relating to the liquid oxygen fill. So you can see them here. First, we have a filter to make sure that any debris or anything that is in the dewar doesn't make it into the rocket, because any tiny particles or debris could potentially ignite because liquid oxygen is very reactive. We also have another orifice. This is to make sure we don't fill the tank too fast for various reasons. We want to control how fast we fill. And finally, we have what's called a ball valve to be able to purge the line. And a ball valve works something like this. You have a ball or sphere that is controlled with a handle, and there's a hole through the sphere, such that if the handle is parallel to the pipe, it's open, and if the handle, you can imagine rotating at 90 degrees, it will be closed and no flow will be allowed. The reason this is necessary because again, liquid oxygen is cryogenic, and if kind of left on its own in a pressurized container, it will continuously heat up, continuously increase the pressure until something breaks, essentially, usually in a catastrophic way. So this ball valve is connected to the fill line, and this allows us so that once we're done filling the tank, we will close the dewar. But before we disconnect it, there's still liquid oxygen in the line, in the hose that connects the tank and the rocket. So we would open this ball valve while pointed in a safe direction, and then the liquid oxygen will flow out of the ball valve and into the air, and then we can safely disconnect it from the tank once it's empty. Next, I'm going to move on to talking about the ground support equipment, or GSE. For us, this is a panel we have near the rocket, and this is where our high pressure nitrogen comes from and our systems to deliver it safely. So if you remember that in order for flow to flow through the rocket, you need a higher pressure upstream. So this is the highest pressure we have. So in a way, it is the beginning of all of our flow. And it looks like this, and this valve here in the diagram is simply a valve on the bottle itself. We wouldn't be able to connect it directly to the COPV. This would be dangerous because the COPV is only rated to 4,350 psi and not 6,000 psi. So if connected it directly, that would be dangerous because it would be above the rated pressure of the COPV. So the first thing we need is an ability to regulate that pressure down from 6,000 to 4,000, or whatever pressure we need. To do that, we have a high pressure spring-loaded regulator. And we also need 2 gauges, one on either side, to monitor it as we adjust the values. And the gauges look something like this, just physical readings of the pressure. We also have an orifice. This orifice is sized so that we fill our COPV at a decent rate. Again, this is so it doesn't get too hot. If we just had no orifice and we filled it as fast as possible, it would get really, really hot, and that could compromise the structure of the COPV. We also have another solenoid, this time on the ground, not on the vehicle. And this is so we can control exactly when we fill the COPV, and so that we can have the ability to fill it remotely without anyone being present on the pad. Again, in theory, this is actually all we need for launching. We'd be able to fill the COPV and launch with just what we have here. But in practice, we want some safety mechanisms in case anything goes wrong or we need to cancel anything. First of which are relief valves. We have 2 relief valves. And what a relief valve is is it's kind of a version of a check valve, but with a much stronger spring. So in this diagram, you can see that if the inlet pressure gets very, very high enough to overcome the spring force, it will open and it will be allowed to be released, in this case, into the atmosphere. And this is just a simple mechanism to make sure that even if the regulator fails or the solenoid fails or if there's any kind of human error, there's absolutely no way that this line, which includes the COPV, will be above 4350, which is the rated pressure of the COPV. This mechanism is our low pressure relief system. So in order to close our fill valve, we need to pressurize the system to about 700 psi while there are a couple members present near the pad. And in order to make sure, again, there's no human error, nothing goes wrong while people are near the pad, we open this ball valve, which is same kind of valve that's down here. We open the ball valve and allow the COPV to be connected to a gauge and a low pressure relief valve. So this is to make sure that the pressure cannot exceed 750 while there are members nearby. When we want to launch, we would close this ball valve, which would separate these two lines and would allow us to pressurize beyond 750. And this would be once the pad is cleared and everyone's at a safe location. Finally, the last two components are our abort modes. In this case, we have two. We have an abort solenoid, which we can operate remotely, just like the other solenoids. And we can do it in case anything goes wrong or we need to cancel testing or launch or anything. And just in case we lose electrical or signal connection, we also have a manual ball valve with a rope attached. And we can physically pull this rope from our safe location and abort the system. And that is all. This is actually the full PNID of our fluid system. These extra components on the dewar are simply part of the dewar itself. Those are not parts we built. To check your understanding, I'm going to go through every slide every second or so, and I strongly encourage you to pause at every slide and try to justify to yourself what the new components are and why they're necessary. And this will help make sure that you really understand where every component belongs in the system. And there we go. If you've done it properly, hopefully you now can understand. If you missed anything, feel free to go back so I can explain it again. Before we're done though, I'm going to go through our nominal procedures and explain which regions are filled with pressure and how our launch goes. Our first step, before any pressure or any nitrogen is filled into the system, we connect the dewar and we connect the ground panel, and then we would open the valve on the dewar. And this would allow liquid oxygen to flow through this line and into the tank. And we continue like this with it continuously venting through the vent valve until the tank is full, which we can see because liquid will start coming out of the vent and it's noticeably different. At this point, the tank is full of liquid oxygen and it's also covered in ice from the outside because it's so cold that condensation is freezing. Now that the tank is full, we want to disconnect the dewar from the rocket. Before we do this, we need to make sure that the fill valve is closed so that liquid oxygen doesn't start pouring out of the vehicle. So in order to do that, again, this piloted line needs to be pressurized to 700 psi. So we need to set the regulator, open the relief control, and open the fill solenoid, which will then start filling the COPV. We do this until it's about 700 psi. And at that point, the fill valve will be closed, and we can safely purge the line with this ball valve, and then disconnect it manually, and then make sure the dewar is safe and stowed. With the dewar disconnected, we can now pressurize the COPV to its full pressure. Before that, we need to make sure the pad is evacuated and all of our checks are good and we're clear to start pressurizing. To do that, we need to make sure the high pressure regulator is set. We need to close the relief control valve so that we can pressurize past 750. And then open the fill solenoid while monitoring the pressure on the COPV remotely. And this will start pressurizing the COPV higher and higher. It usually takes about 20 minutes to pressurize all the way to 4,000 psi. Again, this will be going through the pilot regulator and it will be closing the fill valve. This is to make sure it doesn't start pouring out of the vehicle. But it won't be going through these solenoids yet since all the solenoids on the rocket are currently closed. It will also be going to the inlet of the dome load regulator, but not past it, since, again, this piloted line is still unpressurized. Now that the COPV is pressured to 4,000 psi, the liquid oxygen tank is full or closely full. We are now ready for launch. So we need to make sure it's safe to launch, the sky is clear, the pad is clear, and we start our launch sequence. The first thing it does is it opens the dome pilot solenoid. This will first go through this line and it will close our vent valve, which will officially seal our entire tank, ready for pressurization. And once it goes through this orifice in about a second or two, it will then prime the dome loaded regulator, which will allow flow through the dome loaded regulator and into the tank, which then pressurizes the tank to 700 psi. Assuming our tank pressurization is good, because right now our vent valve is closed, our abort valve is closed, and our run valve, since it is normally closed, is also closed. So our tank is completely sealed. The next step is the igniter goes off. So the igniter is a component in the combustion chamber, which is actually a small solid rocket motor, which essentially sets fire to the fuel. This is a much smaller fire. This does not produce thrust, but it simply gets it burning, ready for the liquid oxygen. And then finally, at T-0, we will open the run pilot. Pressure will flow through this line. It will actuate the run valve open, which will allow 700 psi liquid oxygen to flow through the run valve, through the injector, and into the tank. At that point, you have fuel that's already on fire, and you have 2.5 kilograms per second of liquid oxygen, which is quickly vaporizing and combusting. You will have an explosion inside the tank. You will have high velocity gas flowing through the nozzle, producing thrust, and then the rocket will go up. I hope you enjoyed. I hope this video was helpful, and please leave any comments down in the description if you have them.